We need to go over a few more definitions before we can begin calculating probabilities. The first one is event, and an event is any collection of outcomes from a procedure. Let's go through a few of these definitions and we'll look at some examples. A simple event is an outcome that cannot be further broken down into simpler components. So we have events. An event itself can be a simple event, or it can be more complex. And a simple event then cannot be broken down into simpler components. And then we have sample space. And the sample space is the set of all possible simple events for a procedure. Every possible simple outcome that we can have. So let's look at what we mean by a simple event. For example, a simple event might be a single birth. You know, a couple's having a child, what's the probability that it's a boy or a girl? So when you have a single birth, one possible simple event is that it's a boy. Of course, the other possible simple event is that it's a girl. So that means our sample space, remember it said it's the set of all possible outcomes, all possible simple events for a procedure. So we use this set notation. So the sample space, capital S, is this set, and what's in it? All possible simple events. Boy, and I'm just going to use a B for that, or girl. That's the entire sample space for a single birth. These are the possible, all simple events from this, from the outcomes of a single birth. Let's look now at an event. Now I said an event could be this. This is an event, but events can also be more complicated than that. So perhaps an event that's not simple would be 3 births. So a couple has 3 children, or something like that. And one possible event when you have 3 births would be 2 girls and 1 boy. Well, the reason this is more complicated than a simple event like that is that there's more than one way to have 2 girls and a boy. You could have the girls first and then a boy, or you could have the boy in the middle, or the boy could be the oldest child. So this event of 2 girls and a boy, it could be further broken down into simple events. Each one of these is a simple event, but 2 girls and a boy is not simple because it has these 3 possibilities. Now let's look at the sample space for just 3 births. Well, we could have all boys, or 2 boys and a girl. Well, that's not the only way to have 2 boys and a girl. The girl could be the youngest, the girl could be the middle child, or the girl could be the oldest. And that's all the ways to have 2 boys and a girl. And then we just looked at the ways to have 2 girls and a boy, so we could have the 2 girls first and then the boy. I'm going to have to drop down here. The boy could be the middle child, or the boy could be the oldest. And of course the only thing left now is no boys at all 3 girls. So you see we have 1, 2, 3, 4, 5, 6, 7, 8 simple events that make up this sample space. The event that a couple has 2 girls and a boy is not a simple event because it can be further broken down into these 3 simple events. I wanted to mention the notation here when we talk about the notation for the probability of event. I'm sure I'll show you this again, but we say P of A, for example, and this is read the probability of event A. Okay, so let's look at an example. Flip a fair coin and find the probability of tails. So let's think about the sample space. We're just going to flip this fair coin once. So of course our sample space has two possible simple events. You either get heads or you get tails. Each one being a simple event. The probability of tails, that is a simple event. So we could write it as P of T. Probability of tails. That's how you would read that. And based on what we know about this sample space and fair coins, we would expect that to be 1/2, right? We don't have to even do any kind of experiment. We know what that would be. Okay, we have one more definition in this video, and that is the rare event rule for inferential statistics. And it says, if, under a given assumption, the probability of a particular observed event is extremely small, we conclude the assumption is probably not correct. So let's look at our fair coin example and think about the rare event rule. So if we flip a fair coin and find the probability of tails. So when we say flip a fair coin, what are we assuming? We have this under a given assumption, okay? If you say you're going to flip a fair coin, what are you assuming? Well, you're assuming you have a fair coin, which means you expect the probability of tails to be 1/2. You expect that there's an equal chance that the coin will land on heads or tails. So we're making an assumption that the probability of tails would be 1/2. If after, say, 100 flips, the outcome is that we had 82 tails and, of course, 18 heads. We observed this. Now, our assumption is we have a fair coin. We observed 82 tails out of 100. The probability of that observed event is extremely small with a fair coin. We just would not expect that to happen. So do we, instead of concluding that something rare has happened, isn't that interesting, instead we understand that the problem is probably with our assumption. Not that we just accept this and say, well, that makes sense. It doesn't make sense. So we would say, well, our assumption must be incorrect, that it's not a fair coin. So we'll discuss the rare event rule in this chapter a little bit, and then again when we study inferential statistics.